a structure and constituents of matter, specifically. He did his PhD at the Bachelor at Barcelona University as well, and then later on he moved to Pittsburgh with David Jasno, and then to Tallahassee with everything else. He's been involved in many areas related to statistical physics and complex systems. Just to give a few, he's been involved in pattern formation and frozen fluids, probably he's most well known. Viscous figuring, Casademunt, magnetic growth. Also, he's done some work on bubbles in microgravity, for which we just learned that he got financing from the US Department of State. He's also worked on noise-induced effects, about, for instance, noise-induced transitions beyond the noise interpretation. I've been told that he, although he never came to the institute before, he has made two significant contributions to our institute. One of them was to introduce Pera to the field of stochastic processes. I actually just read that Pera's first paper with Jaume. So coming back, maybe you can write another paper then.
Last one.
And then his second contribution was to suggest or to motivate Damian to push Damian to come here. Since Damian has been a very good contribution to the institute, so we're grateful to him for that. Now today he's going to talk about some noise effects in biology, biophysics, which is a topic that interests me recently, and I guess some sort of good effect of noise in biological systems. Let's go.
Okay. Thanks, Raul, for this nice introduction, and thanks for the invitation to the IFISC. So today I'm going to discuss this work that we did recently in Barcelona. It's a combination of experimental, theoretical, and simulational work. So Javier Orlandi did mostly the simulations that I will be showing. Jordi Soriano and Sara Teller did the experiments, and also Enrique Alvarez Lacalle helped in the numerical simulation. Okay, so I'm going to talk about neuronal cultures. So what are neuronal cultures? This is a physicist approach to complexity in neuroscience, which is just to look for the simplest possible system one can build in trying to learn general principles or these basic building blocks of the physics of neuronal systems. So these are just model systems. Okay, so essentially the idea is to grow some artificial culture of neurons in a plate and see what is the spontaneous behavior they have. So I will not show many of the experimental details because this is Jordi Soriano's work, which I think that some of people in the audience already know. Essentially, you take neurons from an embryo of a rat when they have been differentiated as neurons but not yet developed any network of connections. Then you place them in a petri dish and you have them in a medium where they can live and grow, and eventually, spontaneously, they grow connections, they establish network, and then you start to have electrical activity. So you want to understand these very early stages of what neurons do if you don't have any guide, any biological guidance or regulation of what they should be doing. Okay, so it's okay. So that's how one of these cultures may look like. The bright field image, or in the type of images that we will be discussing, which is calcium fluorescence images, where the brightness shows the electrical activity through the fluorescence of the calcium ion. This bar is 100 microns. Typically, we have thousands of neurons in these systems. Okay, so what is the simplest observation that one sees if you do that? Well, after some days, when they have already established some connection, or before establishing the connections, neurons would fire spontaneously in a completely random way. So they are happy to be living, and they start to have electrical activity completely uncoordinated, and then, essentially, suddenly, after a few days, they start to work coherently. This step from something that is incoherent firing to something that looks very coherent is what we want to understand. So coherent meaning.
Can I ask you a question?
Yes.
Where does the noise come from? When they
spontaneous discharges of synapses. In the synapses, there are some spontaneous discharges of vesicles. That
So there is some coupling already from the beginning.
Okay, at some point they start to be to have synapses. They start to have discharges. Yes.
Okay, it's noise induced by other neurons or some.
No. Well, we'll discuss this.
Okay.
It's in the intrinsic noise, but obviously the connection between neurons has an important role in how this noise behaves. So typically that would be one of these experiments. You see that in this coherent state they fire all together. It looks very synchronous. So if you look at different neurons there on the right, you see that it's essentially like completely synchronous, apparently. Almost periodic, but not quite. So it's very well defined time scale, but not exactly periodic. So at least you would like to understand this first stage of coherence.
Is this real time?
This is not real time. Typically there are 30 seconds between bursts of this type. That's a lot of tens of seconds typically. Okay. So this is what you see. This is what you want to explain. Okay. So to understand what's the nature of this pulsation. Okay. So is there some problem of synchronization? Is there some wave that propagates very fast through the system? Are there any pacemakers that guide this process? Or a very fancy hypothesis that has been going on for a while, which is whether there are leaders. So there are some leader neurons that actually control this process, and the other ones follow. Ultimately, the question is whether this is a self-organized process or a guided process. And if it's self-organized, what's the mechanism? Okay, so that's the thing you want to study. For people working on this, the hypothesis of the wave propagating was not really very popular, but that's what happens. So this is the first part of the experimental work, was first established that there is a wave that goes through the system, so it's not really a synchronization process. So if you actually look carefully in this movie, you can see that it starts at some point and then it follows through the others. To the eye, it's not very clear. If you look carefully to the signal, to the calcium fluorescent signals, you can actually see that it's not completely synchronous. It's not working. Don't worry. Anyway, so if you have, it's only a matter of time and spatial resolution. If you, by brute force, improve your time resolution, you can actually see the wave. Okay, so that's for the community working in these problems was an interesting conclusion. For a physicist point of view, it's not so surprising because after all, this culture is an excitable system. One is used to have waves propagating in excitable systems, so there's no big deal on that.
Excuse me, is urine one of these bright spots? Or?
No, these are collections of neurons. In this example, they are a little bit clustered. But this is just, it's not very illustrative of the typical case. Just that here you can see that there actually, people are not really synchronously firing. You can see that there is A goes first, or B goes first, then goes A, C, and D.
But these are like the two classes, right? Of neurons.
Sorry?
Yeah. They look to me like two unconnected clusters of neurons, or not directly connected.
Well, I mean, don't worry too much about this example. Maybe it's not very representative. So, I mean, we have thousands of pulses of this analyzed, and the picture is the one that I will discuss in a second. So, you can use the statistics of these bars. For instance, is it working now? Yes. This is an important statistics of the IFISC, which is the interval, so the time between these bars. It's actually peaked at some finite value. It's not an exponential distribution. Usually it's more narrow than it looks. It's narrower than it looks here if you have large systems. It's relatively well peaked at some value. And then you can see the waves moving at some speeds. You can quantify all these things. And okay, so the picture is clear. There are waves that are nucleated at some points. The nice thing of having seen these waves is that you see where they start. Then you realize that they start at some specific points. Okay? In this case, we have marked these peaks. We can identify where they start. So then you start to wonder what do these points have in spatial, why are these points the starting points of the waves. Okay. There's another interesting observation, a very interesting one, is the fact that there is apparently no correlation in the order these nucleations occur. So what happens is that it's a very well-defined time scale that tells you when the next burst is coming, but there's no way you can guess where it will start. So you know that it will start, in this example, most likely in one of these three spots, but you cannot guess in which one. But you can guess when it's coming. So you know when it's coming, but not where it starts. This is a puzzle, because if this series is really stochastic, but it comes periodically, okay, you have to really explain this. Okay. By the way, this time scale is well understood. The time scale where between these intervals, the mean value is essentially a scale related to the synapses. So it's the depression synapses recovery time, meaning that when you have a burst like this, it essentially burns out of the system. It takes a while to recover all the vesicles in the synapses. So this time is what fixes actually the waiting time before the next burst. This is just something that doing the numbers is easy to understand, but still is okay. And for people who is familiar with these neuron systems, you have to be careful in discussing whether inhibition and excitation are important in this system, so you can control the degree of inhibition that you have in the neurons. And I will not really discuss too many details of the technical aspects of dealing with neurons. Just the conclusion that I want to state is that the phenomenon is robust. It does not depend on whether there is inhibition in the system, inhibitory connections or not. Some things change a little bit quantitatively, but the phenomenon essentially stays. Okay? So you can see the waves, whether you have just excitation like here or excitation plus inhibition. So this is not really important to discuss the physics now. So the phenomenon is robust, and this is what you want to understand. Where are the bursts initiated, and why does this happen at random? So then you do lots of statistics, and so Soriano did hundreds of these studies, so you can construct a map of probability of nucleation, so of the points where the waves start. And you get that it's quite localized, and you can construct these Lorentz curves where you say the accumulated probability versus the area fraction, so telling you that a small fraction of the area has most of the activity of nucleation activity. Okay, you can characterize all this quantitatively. The important point I want to stress now is that it clearly is a noise-driven problem, because the point where it starts is stochastic. It's distributed, but mostly concentrated on some spots. Okay, so it's a stochastic thing that happens periodically. Okay, so that's the puzzle. So first, why, if the neurons are scattered more or less randomly but uniformly, so there's no really big inhomogeneities in the system, why do you get such a very inhomogeneous behavior? If it's a nucleation process, that's the word I've been using already, it's a noise-driven process, why is it not exponentially distributed, which is the usual thing you would expect by something that it's a nucleation process over some barrier or something? Then the question, why is it really periodic if it's really a nucleation process? If it's random, it's noise-driven, why is it so periodic? So this point, it's if you think twice about this, is not so surprising, because you only require essentially two time scales. If the waiting time between bursts, that's controlled by the synapses depression, is sufficient, is much larger than the nucleation time, then this is what you would expect. So you have to expect a long time, and then if the nucleation is very fast, then you see just a small amount of noise on the EV, on the time between the bursts, but is essentially controlled by another time scale. The puzzling part is that why is it so fast in nucleation? So noise-driven process that is so fast. To give you just numbers, the spontaneous firing rate of neurons is typically in these systems like 0.1 hertz. So you have to have that the nucleation of one of these parts has to happen in the same time scale that if you look at a single neuron, when the time that you have to wait for spontaneous fire. So it's really a very fast process. So that's what you want to explain. Okay. So you have to explain the inhomogeneity of the process and the fast time scale for each worker. Okay, so the mechanism that we call noise focusing is what explains this behavior. So it's really a matter of what are the properties of the noise when they are happening in a network like this. So I'm coming to your point in a second. So then what you do is you do a numerical simulation, because then you can control exactly, first, if all the neurons are identical, because you put them all identical. And then you try to reproduce the conditions of the culture, so you place randomly neurons in a metric substrate. You allow them to make connections essentially to their neighbors, so the network is really Gaussian with a Gaussian degree. It's very simple, very metric, very localized, with what I will call metric correlations, which is essentially the high clustering of the network, and which is saying actually that neurons are connected mostly to the neighbors. They are not really long distance connections. And of course, if A is connected to B and B is connected to C, then A is very likely to be connected to C. So that's essentially a condition. Okay. Now you simulate the dynamics of the neurons. You take from the books, for instance, that's a model from the Zikevich book, a reasonable model for the excitable dynamics of a single neuron. It's really not important now to pay attention to the details. This is a quadratic integrate fire model with leaky integrate fire. So it's some nonlinear equations that produce the excitation of a neuron when you get some input. The important piece is that you don't have only to simulate the excitation of the neurons, but you have to take into account the synapses, so the connections. So that's the dynamics associated to the synapses, which is expressed here. So essentially the current that is injected because of firing, it's some pulse that can be exponential or just a delta function, doesn't matter, but it's rated by some function, which is the depression of the synapses, that is the function that depends on the activity of that connection. So every time that synapse is acting, this parameter B is multiplied by a factor beta, which is less than 1, so it decreases. So if synapses is very active, then it becomes ineffective. And then there's a recovery, exponential recovery of this variable. So this time scale here is essentially the one I said of the mean interval, but you have to incorporate this into the system. So you put these together, you just decide some connections according to these rules, and then you simulate. So the part of the model that is really necessary to understand is the nature of the integrate and fire dynamics, which in general says that a neuron would fire if there are a quorum of n inputs in a certain time window. So as long as you, in a certain time window, you will receive a number of a minimum of n inputs, then this neuron fires. The important point is that I want to discuss not this, say, ordinary firing, but what is called a subquorum firing. So if you have noise in the system, a neuron can fire without any inputs, just because there's a certain amount of internal noise coming from spontaneous discharges of synapses. So in general, you would have that this number of inputs that you need, some they will come in general from other neurons, and some just is an internal short noise in the system. So schematically, you can imagine that a neuron is subject to some short noise that may look like this. So if you have a smaller number than n in a delta t, you don't fire. If you have equal to n or larger, then you fire, and that would be what we call a spontaneous firing, because it's in white, they just put the spontaneous shots of the noise, so that's actually the noise. But you may get some inputs from other neurons, and this adds to the noise, and then it's what we call induced firing. So that would be the spontaneous firing, that would be the induced firing, so the one that combines noise with inputs from other neurons. Okay, so what happens? Okay, you could actually estimate what is the probability to nucleate one of these nucleons, okay, that propagate a wave. You assume Poisson statistics. I will go fast on this because it's really a trivial estimation. The only important point is to understand what condition do you require to nucleate such a wave. So you have to really, like in any nucleation process, you have to have a critical size, then you have to excite, and then you propagate a wave. So you need to excite all the neurons in a critical radius. Okay? This does not mean that all have to fire by themselves, but you just have to excite what is called the critical percolation fraction. So there's a certain fraction of those neurons that if you excite them, then the excitation just percolates to all the others. Okay, so that's something that is easy to understand. Just since you have many connections between them, you only require to excite a certain fraction in order to excite the whole amount of neurons in the neurons. So if you want to estimate this, you have to know what is the critical percolation fraction, which can be easily estimated as the quorum n divided by the output connections. So if you excite this fraction of the neurons, then essentially you will cover all the nucleus. Okay, so the nucleus will have some critical size that we don't know at this point, but you do these numbers, you put them.
How does space distribution come in here? I mean,
Well,
are these
so-
number of neurons being close together? Or?
Yes, these are close together. They are in a metric substrate, and the connections are essentially to the neighbors.
So this critical number of neurons refers to a critical number of neurons in a given.
Yeah, there is a critical nucleus that you can find out from other means. So if you excite sufficiently large, then you sustain a wave. So you have to excite all the neurons in this critical size. So really the condition is you have to excite the critical percolation fraction in that size.
But this size is not in this calculation.
No, this is just NC. Okay? But I mean, the simulations you can just check the numbers and just. It's not really to know them precisely, because if you put the numbers here, then you realize that the probability of satisfying this condition is completely unobservable. You have to wait for the age of the universe or more. Obviously, that's because this estimation is too naive, because I forgot completely about correlations. Okay? So this is just if you consider that only the internal noise is working on this. So this obviously cannot work. You have to do something better. So if you put that model in the simulation and you just plot the findings, that this is what you see. Obviously, you don't have to wait for the age of the universe. After a while, you nucleate one of these waves. Okay? This one came in the center, more or less. The next one comes in a different place. Okay. So this is more or less mimicking the experiment, except that now you see all the findings individually. And you can actually know even more interesting information about from this is the fact that the causal connections between the fibers. Okay, so I will discuss this in a second. And before going into that, let me emphasize a couple of points. Going back to this slide, the first thing that is interesting is that when one neuron fires, for instance, because of spontaneous firing, it projects this activity to the all neurons where it is connected, which may be a large number, maybe 30 neurons. So the effect of the noise is multiplied by a big factor after each of these spontaneous firing. Not only that, but actually this adds to the noise of this other generation of neurons simultaneously. So it introduces also an effect of coherence. Okay. So in all this talk, I will be calling noise not only these primary shocks that come from spontaneous discharges of the synapses, but all the effect they produce just because every once in a while they propagate through the network. So I will call noise all this activity originated by the primary noise. So this noise is the one that will have a very complex structure, which will be responsible for all these effects. So let me comment on these two mechanisms in which this network is actually amplifying a lot this primary noise. what we call this dynamical noise amplification is just saying that you have some neurons firing into this one, so you satisfy the quorum condition, this fires, but if there is a finite probability, if you should only fulfill a fraction of this quorum. Okay? How does the probability of firing depend on the fraction of the quorum? It's a very nonlinear function. So in a course like this just comes from studying the Poisson statistics of the internal noise. But most importantly, so this is saying that if you get a certain amount of simultaneous inputs, then the probability to fire goes up very fast. Since there are metric correlations in this problem, this means that all the neurons that receive an input simultaneously here, which is plotted 3, but then maybe 30 or 50 sometimes, so there will be a subset of these that they will fire. And because there are metric correlations, they will have common neighbors, so they will fire simultaneously several inputs to many neurons. So this means that the probability that you get a certain fraction of the quorum of several inputs is not that small if you have these metric correlations. So you have connections to the neighbors, and you have a lot of clustering in the network. So this goes up very fast, and this is strongly enhanced by the metric correlations. There's another aspect which is what we call the topological noise amplification, and is saying that in addition to the direct connections, you may have a layer of other neurons that construct these feed-forward triangles. So if you consider this motif here, you can actually compute exactly how this probability of firing with a fraction of the quorum goes down with the number of these triangles. For instance, here you have that with 60% of the quorum, you get a probability more or less 1/2 of firing. But this probability of 60% of the quorum, 2.6 of the quorum, goes very fast down if you increase the number of loops of this type. So these loops are not just there, they are just saying that when I'm firing from this neuron to this one, I'm also firing to this one, so this is likely also to fire and could have this connection. So all these feed-forward triangles enhance the probability of this one to fire. So actually, the number of inputs that you need to fire goes down very fast, depending on the topology of the network. So the probability of inducing new firings is much easier than one thought at the beginning. So this, yes?
In this case, let's say neuron C is able to integrate the fires from A1 and B1.
Yes, if they happen almost simultaneously, since there is a time window, it's very likely that the firing from here and from here come in the same window. Yes. So this is an analytical regulation with some approximations, but just to illustrate that this goes down very fast. So this means that with a small fraction of the quorum, you can actually already fire, depending on the local topology of the network. So this can be calculated analytically, as I said. All the more complicated motifs cannot, but you can simulate and realize that the problem is quite non-trivial. I will just show in a second what you get, but let me emphasize before that both mechanisms, if there is a lot of clustering, a lot of triangles between these neurons, the two mechanisms are strongly enhanced. And typically what you would expect is that this noise, that is the primary noise, will generate avalanches of activity, just because of these amplification mechanisms. So what we call the noise, which is the activity generated by this primary short noise, takes the form of avalanches. So that's what it's here. Let me just show for a second in parentheses that one can study different motifs of networks and see how these mechanisms of amplification work. This is for networks that have no metric structure. This is just repeating periodic motifs and just studying, and one can just look at the statistics of nucleation of these motifs, and it depends. Obviously, it's important to have a lot of triangles. The feed-forward triangles help, but also the feedback triangles, a certain amount of feedback triangles help. So it's just, let's say for a moment that this is a complicated problem that can be explored a little bit numerically, and I don't think that this can be solved analytically in any case. But the message is that the detailed wiring, the detailed local wiring of the network has some impact on the ability to propagate or better to amplify noise. Okay. Okay. So let's go back to the problem. So what I'm going to show here now is another simulation where I will not plot the spontaneous firings that do not have any induced firing. So I will plot only the induced firings. So firings that are causally connected. Since I have the numerical simulation, I know everything, so I can construct that. So the picture that I get is a completely different one. I plot a line between two causally connected firings, and I put a different color for a different avalanche. So same color labels same avalanche. Then the picture is completely different than before. You visualize that noise is something that really propagates through the system, something that looks like this. And when the white avalanche appears, that's the big one that will eventually nucleate the burst. Okay? So you can visualize all these avalanches because you have all the information. You can identify the explicit connections that have been causally related. So you get all the details. So once you have visualized the avalanches, you can do statistics of these avalanches. And it's no wonder you get nice power laws here. So you plot the number of distribution of sizes, okay, and you get this beautiful power law. Alpha is a parameter that measures the degree of clustering with the level of clustering given the same connectivity. But it's don't worry for this discussion. So you get a universal power law in principle. You can also plot the durations of the avalanches, so you get this nice similar structure. This exponent can be explained just realizing that these avalanches, when you look at them, they are essentially tree-like. Even though the network is very clustered and has lots of loops, the actual avalanches are tree-like, and then just mapping it to the Kylie tree, which is a network which is tree-like. Then if you're close enough to criticality, this gives this exponent. So this essentially you can more or less explain this exponent. And okay, so that's part of the story. The next step is to try to obtain more information on the structure of this noise. So remember that the original network is really a boring one with just Gaussian degree, local connectivity, just with some randomness, but very local connectivity. If you now look at only the links that have activity over some threshold, let's say the top 5% active links, and you only plot them, then you get something that looks more like this. The colors are the communities that come after analysis of community of this network. So you really realize that there are communities here. But this is just for this network where you have suppressed all the most inactive links. Okay? So what was the degree that was Gaussian, it looks more like a scale-free. Okay? So that's because you have put the dynamics here. Okay? So the dynamics have essentially turned this Gaussian network into something that looks more like a scale-free. Before that, let me insist that this you may call this a functional network, but this is really not the original network. Okay, so this is an effective network that you get just focusing on, just concentrating on the most active sites.
Can you repeat how do you construct this network?
So you take a time average of the system, and you suppress all and you only keep the links that are more active, most active.
But time averaging in which window?
Sometimes. Obviously, you cannot do it for infinite time because this eventually nucleates into a wave. So, but during all the process before nucleation, you have many avalanches. You could construct a network like this for every size of avalanches, actually. But the one that I'm plotting here is just focusing on all the avalanches, but just keeping the links that are most active. And this already is quite inhomogeneous, although not as much as we expect for the nucleation process, but at least this already gives a non-trivial structure even by the interplay between the dynamics and the topology.
But then the communities that you identify there,
That's for the effective network.
it has a topological property.
Yeah, of the effective network. Yes.
Nothing to do with correlations of the activity
No,
of the
no.
different
So from the dynamics, you construct the effective network, and then you do a community analysis of this network, and you see these communities. But now,
why do you call that functional? Why do you call
well,
that
some people,
functional?
you could call it effective.
No.
I mean, for the purpose of nucleation, we will see that this is relevant. So this is saying that if you just have this thing, you have already the effect. You can forget about all the other stuff. But yeah, functional. We will discuss.
But it implies other things.
Sorry?
Okay, normally functional implies other things.
Depends on the context.
Yeah.
I mean, in neuroscience, they would call this easily a functional network. Okay. So what can we do now is forget about this nice structure and just look at the process of nucleation that was the object of study. So there will be some of these avalanches that will eventually nucleate one of these ways. We call these ignition avalanches. So it would be in principle large avalanches, but not only large, because you can have large avalanches that are very extended and then they are not able to excite the critical percolation fraction of a given nucleus. So you need to have, there's a subclass of avalanches that we call ignition avalanches that are sufficiently large and sufficiently concentrated in space and time so that they can excite the critical percolation fraction. Okay? In general, they will originate in larger areas than just the nucleus. What I call NC is the number of neurons in one of these characteristic nucleus. So they will receive activity from larger regions, as we saw already in the simulation. So there will be in general a probability that spontaneous firing generates one of these ignition avalanches. So that would be the non-trivial object that we don't know how to calculate, but if you know how to calculate this, then the nucleation rate is distinct. Number of neurons involved in this region, spontaneous firing rate, times this probability. So what we are saying from the experiments and from the theory is that this quantity here is of order 1. Just in order to explain the experiments. Okay? So this is saying that it is relatively likely that you create one of these large avalanches that nucleates the system. So the nucleation rate is related to how easily you generate one of these avalanches. Of course, you can do also statistics of many different things. This is just showing the explosive nature of the process. So it goes exponentially to the point of ignition. Now you can do all these statistics, but the point that I want to discuss is another one. So that would be a map of nucleation probability. So you, like the experimental ones that I showed before, this is from a certain simulation. So this is a contour map of the nucleation probability. As you see, it's very concentrated in a few spots. That's the effective network that you would obtain if you just consider the ignition avalanches for this specific network. So you don't take all the time averaging of all the activity, just take very large avalanches, or more precisely the ignition avalanches. So you get some network. You also see these communities, but you don't really have a very good match between these two maps yet. Because, okay, here you see two communities, but here it looks like the one here is more able to nucleate than this region here that will be here. Okay, and the plot here does not look that much like this. There is something here that resembles this, but it's not really so good. In particular, if you look carefully to this point, you see that if you just do the time averaging, you will see that this part and this part are more or less equally active. But if you look here, you would realize that this part is more likely to nucleate than this one. So this one is more likely to nucleate than this one. So this means that there is a net flow of the activity from this to here, from this side to here. So even though the two have a lot of activity, this activity here is more likely to end up in this region than the other way around. So this means that additional correlations that we missed here, because by doing the time averaging, we're just looking at correlation between different parts of the system, but now we realize that we should be looking at spatio-temporal correlations, because this is saying that there is a net flow from this region to this region, okay, that you don't see here, but you infer from here because this is more likely to nucleate here. So time correlations are also important. So this brings the discussion to the summary that is, that's what I just said. The spatio-temporal correlation are still missing, so I'm going to discuss now in detail this slide, which more or less summarizes the situation and gives the way to the actual answer to the problem. So this is another example. What I plot here is the probability of nucleation of these waves. Okay, so there are essentially two spots here. Now we try to correlate this picture to different observables that I can do. For instance, I look number of triangles. It's not exactly the clustering of the network, it's the number of triangles per neuron. So I put this in a contour map. I don't see very nice correlations here. For instance, I see here a point that has a very strong clustering that has essentially no effect of nucleation and all the differences. Okay, so this is not a very good observable. Now I do some time averaging of the activity, like I did for the effective or functional network, and I count the regions that are more active, so that would be more or less the communities of the effective network. And again, I don't see, I see some resemblance, but I don't see really a strong correlation. For instance, I see here a point that has a lot of activity, but it's an activity that does not end up in a nucleation at this spot. So it maybe starts here and goes somewhere else. There's no signature of this spot here. Okay? So this is also not a good observable to explain this picture. Now I go to this one, P. One could think that this is a smarter observable because this is dynamic. This is the percolation fraction, the local percolation fraction. You would tend to think that if the percolation, the critical percolation fraction is smaller, it's more likely to nucleate there. But again, there's no very good correlation between this map and this one. Okay? The final panel is D, but let me go first to F. So this is just a way to quantify this focusing or this concentration of the activity of nucleation in these Lorentz curves, these curves that look like the ones I showed before from the experiments. So when you plot the accumulated probability versus the area fraction, so this is measuring how concentrated is this activity. So a straight line is just saying that everything is uniform. So these two lines are for different levels of clustering of the networks, the concentration of the nucleation activity. So this is saying more or less that 20% of the area accumulates 80% of the nucleation activity. So that's the concentration, the high degree of inhomogeneity of the network. Okay, this line here, this is just the intermediate between these. This is a straight line, and the one that is close to the straight line is just these observables here. So these really are not very inhomogeneous. This one is just the nucleation score, the ignition avalanche score measures the participation of a neuron into ignition avalanches. So this is intermediate. This is just saying that the areas which participate in an ignition avalanche are large, are not as are relatively large, are not as concentrated as the nucleation process itself, but are large. Okay, so this is saying that the reason for this concentration of nucleation involves and must invoke regions that are large. We'll see this in a second, but that's the interpretation of this. Anyway, so there's a clear separation between the actual spatial concentration of the nucleation and the inhomogeneities of all these observables. So the picture that is the correct one is this one here that I will plot again larger in another slide, and is the following. As I argued before in that map where I was invoking the spatio-temporal correlations, actually there is, on the average, when you look at the ignition avalanches, on the average there is a net flow from some regions to other regions of this network. So you can actually average this activity. So you filter the small avalanches, you get the large ones. You do an appropriate average of this, and then you get an average flow of the noise. Remember, this is the effect that originates only in the noise, and it's amplified to the system. When you average all the disorder, all the fluctuations, you get a flow field, and you can construct the streamlines of this flow field, and they look like this. So the streamlines obviously concentrate exactly at the points where you see the nucleation. So what is this saying? So the question one would like to answer is, what is special? What makes a region special in the sense of being able to nucleate of these waves? We've seen that it's not really a local network property, because any simple observables that we check do not really correlate well. There's not even a local dynamical property, because the local propagation fraction also did not do the job. It's truly a non-local collective phenomenon involving relatively large areas. So what really happens is that when you construct this effective flow from the ignition avalanches, from the large avalanches, you realize that these spots of nucleation happen to be at the confluence of the streams of the flow of this effective flow of the noise. So there are some paths, some streams where the amplification of the noise is on the average favored, and so this on the average will produce a net flow of the noise. Okay? So there is the amplification of the noise is directional in the system. It's very sensitive to local details of the network, but eventually this produces streams, flows of noise. These streams happen to end up at some points. So the sinks of this flow are the nucleation points. So really there is nothing special on these points except of being at the confluence of streams of large amplification of the noise that obviously depend on details far away from this point.
I got lost. This is a property of the microscopical network of synapses, or a property of the functional network you mentioned?
No. I forgot about the functional network. So I have my system, my original network, all synapses. I do the simulation, complete simulation. I don't do any tricks. I do the averaging, which is the most tricky part, but I do the averaging, filtering the small avalanches. And I get that on the average, if you look at some point, there is a net flow. I didn't put the arrows here, but obviously there are arrows. There are places where the noise is preferentially amplified and more largely amplified than in other places. When you construct this flow field, then you just propagate this field, and this ends up at some things.
Is it a static thing or a dynamical thing?
It's an average thing. This is an average of the flows, but this contains effectively the spatio-temporal correlations, because this is saying that high activity here goes preferentially in this direction. That's what this is saying on the average. So, but this is just numerics. This is analyzing the numerical data. There's no theory. I mean, theory is the next step, but
the next finding is approach will be completely different.
Yeah, I mean, if you look at the single realization, you would not see this. You have to do averaging of many realizations, and then you see this amount. This is just saying that if you are at this point, it's very likely that this will be amplified the noise, and it will go in this direction. And then obviously, if you've received also a lot of flow from one direction, it's more likely that you would also propagate again in that direction. So this is the result of all the collective activity. Okay. But this is very highly anisotropic. Okay. But this map does not correlate at all, or not very well, the actual arrows that you have in the network, because you have arrows in all directions. This is selected by the amplification, so this is a dynamical effect of involving interplay between dynamics and topology, but this is dynamic.
Jaume, when you speak about several polarization, is with the same, let's say, culture?
Yes. But this is all numeric with the same realization of the network, but then with hundreds of realizations. So the picture is the referees were hard on that, so we had to do a lot of statistics, but it works. It works this way. So the nucleation points are these things. So really, one have to picture the noise in this system. So it's local noise that is really propagated and amplified through the internet and fire dynamics. You have to picture as something that is really flowing. And what is really selecting the reactions is the ability to amplify this noise by the local properties at every point. But it's really not a non-local process because it involves the fact that here you have a large probability to project in this direction also is because there is flow coming from this side. So it's really correct. You could always think, well, you did not really try all the observables. Maybe there is some local observable that also maps these things. So we just tried. I just show you some examples. Of course, this can always be argued, but you can rule out this possibility just making some tests. For instance, this is just an experiment. So you construct the probability map like this, and then you cut some part of it. Okay. So then, if you cut this part of the culture, then you realize that obviously you lose this thing here, but the shape of the probability of nucleation in this region has changed, even though you modified the network relatively far from that. So really, this more or less illustrates, if not proves, that what happens in this spot here depends also on part of the culture that are very distant. Okay? Obviously, if you do it the same in the simulations, you will get the same thing. So that would be, how much time do I have left? So this is 1 hour? So let me go fast. You can try to now construct an effective model for this flow, not really the underlying network, but just construct it. Treating this like excitable system, let me just mention that what I'm trying to argue is that the noise in a system that has this underlying network, even though the network is in principle rather trivial, must be modeled in a very different way than usual in the continuum equation. So really, what I plot here in this red square is all the terms that are produced by the noise. So we have some variables. Don't worry about the meaning of these variables. This is essentially the activity. So I have two new parameters. Well, let's call it transport parameters. So there's an amplification, local amplification on the average of this field just because of the intermittent fire. But also there is vector field B that in principle depends on the underlying network, but it's not just built in the network. We need the network plus the dynamics to figure out what this is. And this is what produces effectively these straight lines of flow. So really the activity is advected through some non-trivial field that you must construct knowing the network plus the intermittent fire dynamics. So this is the model we're working on now, but we'll skip the details. So it's just extending usual excitable media theories to a three-variable system because you have to take into account, say, depression. So notice that the spatial coupling is Laplacian here, for those who are familiar with excitable systems, is actually killed if omega is equal to 1, so when the network is depressed because there has been some burst or something, is killed. So really you lose the spatial coupling because you lose the connections if you have all the synapses exhausted. Okay, so there's an additional variable that takes into account the dynamics of the synapses, but other than that, essentially is the noise that is really different. So you can actually do a simulation of this.
But B is a parameter independent of space and time?
In general, it would depend on space and time, both space dependent. So B for sure. Alpha, you can take maybe the average. Both are, B is a vector field. It's a vector field. It's actually what produces this structure that I was.
So it is like a convective amplification of noise, but with a convection which is space and time dependent.
A convection? No, it's not space dependent. It's only space dependent, not time dependent, and it informs of the underlying network, but it has also dynamical information.
So the question is, how this underlying
network appears. Because of course, I mean, you at the beginning had these nucleation spots, and you infer that these nucleation spots appear because it's the sinks of this flow of the noise.
Yes.
But, well, originally, this sink happens, you don't know what is going to happen, and then it turns out to happen at a precise place.
Yes.
So you can rephrase the question, the original question again, why that particular place is a sink for the noise.
This is an unsolved problem. Yes. So I'm saying this. You don't know this a priori. This is just phenomenological approach. So this is like a transport parameter. You don't really know in principle what is the transport parameter. You have to do the connection between the microscopic level and the
But there is no model, say, for the period, for the how this effective network of how this effect is transported.
Well, the first naive guess would be, let's construct a vector field B from the network. Since your network are vectors, and you do some averaging of these vectors, and this is not completely nonsense. You get something that is similar, but it's not the whole story. It's not the whole story. But to a first approximation, one could easily construct a B like this, just averaging the network. But since there is more than the network, it's also the dynamics. But it's the dynamics of the noise. So this whole thing is how the noise is, if you want, renormalized in this equation. So you have some additional randomness, but the noise produces these two terms. That's what I'm saying. And obviously this V depends on the details of the network. It depends strongly on the details of the network. Yes?
You try to use spatially ordered noise, so instead of completely stochastic noise processes, to see how the structure actually superimposes.
You're asking if I tried? No, I didn't. No. So what do you suggest? Or?
No, but to me it seems like right now the question is how to tell the two effects apart. So what's actually global, or what creates the sink? The structure of the network, or also the dynamical properties of the noise at this current moment?
No, it's a combination of the two.
So then you would introduce a structured noise, let's say like this.
Well, our first attempt to try to pursue this question is this motif that I showed you before. So you construct some network with some control properties, and then you put these dynamics on this motif, and it's a mess. You really don't miss. At least we could not get anything out of that. You do the simulation, and what you realize is that you change a little bit the wiring, and you change completely, or you change sensitively the amplification of this. So it's really very sensitive to the wiring, but it's not easy to correlate how to have to change the wiring in order to improve the amplification. No. I mean, the obvious thing is to try simple networks. Right? This is what we did, but these simple networks with this interfere dynamics are still too complicated for us.
I was thinking rather leaving the network the same, try to propagate excitatory waves, for example, and see how they propagate.
Well, I did not try. Sorry, I was just showing. Is this right? Yeah. So this is just illustrating this model. So you have the depression time between. You see that it's not nucleating at the same spot.
But it will only nucleate at the same spots. There are 2 or 3 spots where it nucleates.
That's it. And if you go to there and you look carefully, you don't really see any special difference if you just look at the network. So it's really a matter of you have to look at properties in a large area. And yes, but still, I mean, for us, this is not easy to get anything out of this. So now the slide for the sociophysicists here. There's a direct analog of the integrated fire dynamics in what is called the illusion of truth effect in social sciences, which is saying that if you hear something many times in a short amount of time, you tend to believe that it's true. So in the rumor propagation problems, you can apply a rule like this. So imagine that you only propagate some rumor when you hear it several times, and you then grant it credibility, and then you're done. You're exactly in the same situation as the neurons. Maybe the topology is not the same, so maybe you don't get waves that are so much localized in space, but the process of nucleation of rumors in this case, I believe it would be the same. So the avalanches activity will be there also, and the initiation of the waves and the places where these are initiated would follow similar rules.
Well, there is a big difference, I mean, because not all rumors are the same, but all the findings are exactly the same. So you have this accumulation effect, while in the other case, if you randomly start a rumor, will be completely different, and there is no chance that you're able to repeat just by noise, invent a rumor that is exactly the same as somebody else. So this accumulation effect is not going to be there.
Yeah, you mean that the primary noise is every time is a different rumor, or you should have many people inventing the same rumor at the same time. Okay. We did really not work out this analogy. It's just at least the integrate and fire dynamics is there. Okay, so the conclusions are this one. So this coherence spontaneous activity, so that's something for the community of neuroscience. Does not require leaders, which was disappointing for many people, but really without any special neurons you get this behavior. Noise is structured in avalanches without similar statistics. We can construct different effective networks with different criteria based on this. Interface dynamics, integrate and fire dynamics, plasmametric correlations. This leads to this strong spatio-temporal localization of the noise activity, which is what explains this concentration of the nucleation process. So this is what we call noise focusing. So noise really flows through the system and concentrates at some points, even though the network is essentially very homogeneous. So the key is the strong sensitivity of the noise amplification to network details, which defines actually this non-trivial flow that is inherently collective and non-local. And maybe there are implications to social networks, but at least to network reconstruction, yes, which is meaning network reconstruction refers to infer properties of the network from the activity of some dynamics sitting in the network. So in this case, we're saying that if you look at the activity, you would essentially see what we call the functional network. You will not see the actual network. It's maybe more interesting, I don't know, but there's an issue here on how to really reconstruct network information from the activity. Okay, so this is my co-workers, and thank you very much for your
I have a question concerning your assumption at the very beginning of your talk. You very strongly emphasized that this effect obviously is noise induced. And while I can imagine that it's very well possible, I saw most of the things you presented actually do not rely on the fact that it's noise. What, for example, at what point could it not just be, for example, spontaneous, complex behavior of the network coming from the connectivity of your network, which is kind of because what you call noise flow or noise amplification. You could rephrase it as fluctuation amplification or fluctuation flow. So how far does it really require the noise, because that might impact the interpretation of the mechanism that are underlying to this process?
Well, at least I can say that the sequence of firings is completely uncorrelated with very strong statistics. Okay, so
but that would hold for complex behavior as well.
Yeah, this is one part of it. The other part is that you actually put noise in the system and see exactly the same thing. Okay, so yeah, it's not ruled out that maybe this is some nonlinear effect. But
we see, for example, in other dynamical systems that noise modeling of the deterministic effect nicely, for example, reproduces the correlation propagation properties like that.
Okay, maybe we were biased, but at least when in the simulations when you know exactly everything that's going on, you put noise and then you see these things. If you don't put noise, you don't. Then you may say, okay, noise is just something here, but then it's another stuff that's going on. But I tend to think that I just call noise just all the activity that is triggered locally through avalanches. So if you want, we can call it avalanches. And then avalanches are there and are relevant for all these dynamics. So if you want, we can call it avalanches. But I wanted to call it noise, not because I used to work on noise for a long time, but I think that it's really, I think it's the proper way to think about it. The noise is more or less homogeneous everywhere, but because of the connections of the network and the way it's amplified, it happens to propagate in a certain pattern, and these patterns just happen to concentrate at some point. So essentially, you see. And I guess that one could think, to what extent this is relevant to actual neural tissues, because this is very far from our brain, for instance. The answer is, of course, there are many things going on in the brain and in other tissues, but what we're saying is that this primary behavior is there, so the noise conceived in this way is amplified also in this way, and either the actual tissues take advantage of this or suppress this, but this is there. This is just the physics, the spontaneous physics of neurons connected with anything else. So that's what the neurons will do. So if you don't want this, then you have to cancel or tame this tendency, or maybe you can take advantages in some cases. But the point is that this is physics, this is there, and then the real biological tissues have to deal with this.
I missed something that I think is very important in this talk, is how do you calculate the lines of flow in this average activity pattern? I think.
Well, the lines are easy. The thing is how you construct the vectors. Because then, once you have the vectors, you construct the lines. The lines is just to visualize the well, there are different ways of doing it, but essentially what you do is you average the activity. So,
how do you get the line? I mean, I understand the density plot you have. I mean, there's things which are firing more often, and things which are firing less often.
A simple way to getting it, which is not the most. Is the first we tried, is just you construct a vector, just looking at where the activity, since you're concentrating only on ignition avalanches, so you know where the avalanche goes because it will end up at the nucleation point. So you really have a direction already from the beginning. You start the noise here, and you know that the avalanche ends here. So this already gives you a vector. You can try to do this maybe more carefully by just not looking at the end of the avalanche, but just the avalanche after a while when it has grown. Okay. It gives essentially the same thing. So there is really a direction just built in the fact that you're concentrating only on ignition avalanches. So you know that these avalanches end up at some point where the avalanche is, the burst is initiated.
You put tail lines going.
No, I mean in this way you construct a vector at every point. So then when you have a vector at every point, you just follow the lines. This is just software to plot the lines. The difficult part is to have a vector at every point.
How does your interpretation now support the time scale in your new system?
The time scale between bars is the synaptic depression time. So when you exhaust completely the depressions, because when you have these bars, every neuron fires many times, so you completely exhaust the vesicles of the synapses. And then you have an exponential time that I plot the equation at some point, the recovery of the synapses. So when you have a burst, everything is burned out. You have to wait for a time to recover the synapses. So that's the time scale between the bursts. The thing is that when the synapses are already recovered, then in a much faster time scale you have these avalanches that eventually nucleate in ignition.
You mentioned that when you change a little bit the topological network, the structure of all this flow avalanches changes. So it means that, of course, this of course depends on the topology and also on the dynamics because it's an effective way. Now my question is, how sensitive is this to the dynamics itself? So if you change slightly the parameters of the dynamics, or if you change a little bit the model, does keeping the topological network the same, does the flow changes a lot? I mean, have you, because
it's not sensitive to the dynamics of the neurons themselves, and not sensitive to the dynamics of the synapses. essentially the proof is that in the experiment the dynamics is not exactly the same, it's different. It's essential. I mean, of course, what you have to have is a range of parameters. No? The meaning connectivity has to be sufficiently large. The clustering has to be
not the fact that not the fact that the streams appear. The fact that the streams are located at that precise place. I mean, you say that these changes are one with the structure and also with the dynamics.
This is very sensitive to the rewiring. The problem is that
to the rewiring, no, to the dynamics. If you change one parameter of the dynamics, because this is something that is an interplay of topological properties and dynamical properties. I mean, usually one checks against the topological and say, yes, topology makes a big role because if I change the topology, it changes. Now, question is,
I understand.
How much is the role of the dynamics?
We did not change the parameter. I don't expect much sensitivity, but I don't know. Really, the rewiring is really very sensitive. The problem with the rewiring is that if you just rewire at random, you change many properties of your network. So you want to rewire in a way that you keep more or less the same clustering, the same connectivity. And if you want to do that, then it's complicated. So what we did is just study motifs where you are not really in a metric space and just look at the topology. And it was already very sensitive there. So, but yeah, I don't know the answer to the question. I don't expect much sensitivity to the model.
Which would mean that at the very end, if that's the case, then the main property that determines the places is the topology. Although it's not just the topology, if it is more sensitive to the topology than to the dynamics.
Yeah, you're right. If you know how to correlate the topology with some dynamics to the actual result, then you should be able to guess, given a topology, what would be the flow. Yeah, that's right. But this is just being able to construct this vector field, this transport coefficient I was saying, from the network. Yeah. That's the non-trivial part, but again, transport coefficient.
Yeah, I'm wondering if you try to relate the vector field that you compute with more structural properties of the network, like I don't know, skeleton, or like more naively, if the seed of these avalanches are nodes with highly betweenness, or even just halves of the networks.
So this is what we tried in the examples that I was showing. The first thing you try is the number of neurons, or the density of neurons, or the density of connections. This does not do it. Then the density of triangles. This does not do it. We did not continue in checking these things because then we realized that it was very non-local. But in principle, we did not check all the possible neurons. We check only the obvious ones: density of neurons, density of connections, density of triangles.
Right, but there are some measures that also capture like flows in the network, like this skeleton or the node betweenness.
Yeah,
that could be more relevant to this.
Yes.
Now, last question, Margarito.
Easy. The averages are sensitive to the initial condition.
The average is the initial condition.
I mean, if we,
the answer is no. Because you do many realizations of this.
It's not for the same network, because you have to identify.
You have a condition in the same network.
Yeah, because you want to identify. Well, I don't know. Maybe depending on how you start, you have some memory on the process, and the scenes could change place. This is what I want.
No. That's not the case. So you can start. There's no memory. Every burst is essentially uncorrelated with the past. So when you exhaust,
you have some refractory time for the neuron, so somehow
that's
you
right.
cannot go backwards to maybe there was something.
Well, but but you're talking of sensitivity of the final map of nucleation.
Yeah, whether that is sensitive to how you started the simulation.
I don't think so, because we ran several times with the same network, and we get. It's not a single run. So we did many runs with a given network. So no, that's no. But I no.
And you try and move on. Again, there are other questions. I think we should stop here now. Jaume will be here today and tomorrow morning. He will be just after lunch. You need to talk with him. Something else. He's in Joan Salaz's room. And he'll be giving a sociophysics seminar tomorrow at 10:30. Okay? All this.
Well, I will listen.
That's what you've been told. all. No. Okay, thank you again.